Get out early. Okay, so the last piece of discussion related to enthalpy of reaction is going to be about enthalpies of reaction from standard enthalpies of formation. In this lecture, we're going to break down what we mean by standard, and then we'll get into the enthalpies of formation. So what have we discussed? We have discussed calorimetry. Calorimetry is how you would determine enthalpies experimentally. We've discussed Hess's law. Hess's law is how you can infer enthalpy based off of a series of reactions. And we have discussed bond enthalpies. Bond enthalpies are a way of estimating the enthalpy of the reaction. Now we're going to get into calculation of enthalpy using standard states of formation, standard enthalpies of formation. So the very first thing we need to discuss is what it means to be a standard state. Well, it's dependent upon the state of matter. If it's a gas, then a standard state is going to be at 1 atmosphere of pressure. If it's a solid or a liquid, it means that it's going to be at 1 atmosphere of pressure, and at 25, most of them that we're going to work with are going to be at 25 degrees Celsius. And if it is a solution, meaning it's aqueous, then it's going to be a 1 molar concentration. So again, it depends upon the state of matter. A solid, it's 1 atmosphere. Liquids and a gas, it is 1 atmosphere. Liquids and solids, it is 1 atmosphere and 25 degrees Celsius. And then for a solution, an aqueous solution, we are talking about 1 molar in concentration. So that's what we mean when we say standard states. That's what we mean when we say standard enthalpies of formation. They're going to be enthalpies of formation based off of these standard states. So a standard enthalpy change. Delta means change in. What does delta always mean? Final minus initial. So we're talking about the change in enthalpy for a process when all reactants and products are in their standard states. That's, again, what we mean by standard. You will notice that the naught symbol is attached to that enthalpy. That naught means that it's a standard state. So anytime you see delta H naught, or in College Chem 2, you'll see delta G naught, or you'll see delta S naught. We're talking about standard states. So again, we're going to be dealing with the change in enthalpy for a process when all reactants and products are in their standard state, when we're talking about standard enthalpy changes. So one of the ways we describe these standard enthalpies is by their standard enthalpy of formation. What we mean is we mean the formation of a pure compound from its constituent elements in their standard states. Now, what that means is, and for a pure element in its standard state, it's going to have an enthalpy of formation equal to 0. So because we're talking about 1 mole of compound from the elements in their standard states, and the elements in the standard states is 0, that means that what we're observing when we look at the enthalpy of formation for the compound is we are looking at the enthalpy of formation for that compound. So it's our way of deriving and determining enthalpies of formation. So let me just give a reaction and discuss it in greater detail. Carbon solid graphite plus 2 hydrogen gas goes to make methane. This reaction has a delta H of formation of a negative 74.6 kilojoules per mole. Because carbon solid graphite is an element in its standard state, it has a delta H of formation equal to 0. Because hydrogen is in gas form, it has a delta H of formation of 0. So this negative 74.6 is entirely due to that 1 mole of methane. That's what we mean when we're talking about the delta H's of formation for 1 mole of compound from elements in its standard states. It means that that value is solely associated with the compound. Now, a lot of work has been done to determine these enthalpies of formation, these standard enthalpies of formation. And in fact, you can look up the standard enthalpies of formation by going to Appendix B of our textbook, or you can look them up online by simply searching for standard table of enthalpies of formation. So if you're doing homework and they don't give you the enthalpies of formation, all you got to do is go online and look up table of enthalpies of formation. Or if you have a textbook, you can look in Appendix B. Now, for this lecture and for the optional homework, I looked up the standard enthalpies of formation, and I believe I've written on the homework, I believe I've written them directly under the substances. So let's talk about how we use these standard enthalpies of formation in order to find the enthalpy of reaction. The enthalpy of reaction is calculated by subtracting the enthalpies of formation of the reactants multiplied by their stoichiometric coefficient from the enthalpies of formation of their products multiplied by their stoichiometric coefficients. What does delta mean? I keep coming back to this. What does delta mean? Final minus initial. In a reaction, what is the final? The products. That's why we do the products first, minus the initial, which are the reactants. So we haven't changed the meaning of delta. So again, the enthalpy of reaction under standard states is going to be the sum of the moles of products times their delta H of formation minus the sum of moles of reactants times their delta H of formation. That's the take home. The words are just simply saying what that equation states. That's the take home. So let's look at some examples. Use the standard enthalpies of formation to determine the enthalpy of reaction for the reaction of ammonia combining with oxygen to form nitrogen monoxide and water. Folks, when you're looking up the enthalpy of formation, one thing that you need to remember is you've got to pay attention to the state of matter. I went ahead and illustrated this because ammonia gas is a negative 45.9 kilojoules per mole, but ammonia aqueous is a negative 80.29 kilojoules per mole. You got to pay attention to the exact state of matter you're working with. Oxygen gas. Oxygen gas is going to be 0 because it's an element in its standard state. And all elements in their standard state have a value of 0. Nitrogen monoxide is 91.3 kilojoules per mole. And again, you've got to pay attention to water. It is, for gas, a negative 241.8, but for liquid water, it's a negative 285.8. So, number one mistake students make is they don't pay attention to their state of matter. The second mistake that students make is they forget what delta means. And they try to do the delta H of reaction in the same order as its reaction, but you can't. Delta means final minus initial. So it's the products minus the reactants. So let's look at the math associated with this. My delta H of reaction in its standard state is going to be equal to the sum of the products times their stoichiometric coefficients. So I have 4 moles of NO times its delta H of formation, which was 91.3 kilojoules per mole, plus I have 6 moles of water in gas form times a negative 241.8 kilojoules per mole. That is the final, because that was my products, minus the initial. I have 4 moles of ammonia in gas form times negative 45.9 kilojoules per mole. Plus, I have 5 moles of oxygen times 0 kilojoules per mole. The reactant side, the product piece comes out to be a negative 1085.6 kilojoules minus the reactant side, which is a negative 183.6 kilojoules. Doing this math, you get a value of a negative 902 kilojoules as the enthalpy of reaction under standard states. Yes. You are given a table that you can look it up on. It's actually, this table is embedded in the problem, so it's right there. But yes, I give you the standard enthalpies of formation in a table for you to look it up. Other questions? Let me give you one to do. This is the thermite reaction. I'm trying to make sure that you can see it as well as I can do it, as well as I can get it pulled up. Which is two aluminums react with iron 3 oxide to form aluminum oxide and two irons. What is the enthalpy of reaction for the thermite reaction? So you should have gotten a negative 851.5 kilojoules. it was the 1 mole of aluminum oxide times negative 1675.7 kilojoules per mole plus 2 moles of iron times 0 kilojoules per mole. From that, we subtracted 2 moles of aluminum at 0 kilojoules per mole plus 1 mole of iron 3 oxide at negative 824.2 kilojoules per mole. So it was a negative 1675.7 minus a negative 824.2, and that equals a negative 851.5. Questions? Let's look at another one. Let's look at the burning of octane. On this one, you should have got a negative 10,148.2 kilojoules. Again, it's final minus initial. So it's the product minus the reactant. So I took the product of 16 moles of CO2 times negative 393.5 plus 18 moles of hydrogen of water times negative 241.8. And from that, I subtracted out 2 moles of octane at negative 250.1. The oxygen contributed 0 to that because it's an element in its standard state. And therefore, when I put it into the calculator, I got a negative 10,648.4 minus a negative 500.2, which meant it was a negative 10,148.2. Questions? Compared to Hess's law, this is easy. Hess's law, I expect to be the most challenging of the enthalpies of reaction. Yes.
Are we going to do the second part of that question?
So let's see. I did have a plan, yes. Okay, a city of 100,000 people uses approximately 1.0 times 10 to the 11 kilojoules of energy per day. Suppose all of the city's energy comes from the combustion of liquid octane to form gaseous water and gaseous carbon dioxide. Use standard enthalpies of formation to calculate the delta H of reaction for the combustion of octane and determine how many kilograms of octane are necessary to provide this amount of energy. The fact of the matter is remember from our previous discussion, this negative 10,148.2 is associated with 2 moles of octane. So we can take, and I'm going to do it above the mark so that I can show it. So we can take this 1.0 times 10 to the 11 kilojoules. And we can use what we just calculated, which is for every 2 moles of octane, it is a negative 10,148.2. Now, technically, it's just 10,148.2 here, kilojoules. The reason, because what does the negative technically mean? Heat given off. So when we're talking about it, we're talking about the same thing here because we're using approximately and and it's given off. So then what you need to do is you need to convert that into grams. Using the molar mass of octane, which I'm making sure I keyed into my calculator right first, which 1 mole of octane is 114.26 grams. And we've been asked to convert that into kilograms. So 1,000 grams is equal to a kilogram. So this comes back to that stoichiometry we discussed in the laboratory. And when you key this into the calculator, you get 2.25 times 10 to the 6 kilograms. So yes, I wanted us to do the second part as well. Because I want us to come back and remember we can do stoichiometry with our energy. Questions? Okay. So that takes care of enthalpy of formation. The last thing is coming back to this concept of lattice energy, which was on exam number 2. On exam, actually, we've been building up, and the reason I want us to show lattice energy is because it's a buildup of several things that we have already talked about. Back on exam 2, we looked at the trends in lattice energy. And we said, if you had a +2 cation and a -2 anion, that is going to result in a much larger lattice energy than would a +1 cation and a -1 anion. That was rule number 1 for us. The larger the charge, the higher the lattice energy. Rule number 2 for us was the smaller the size, the higher the lattice energy. So once we had sorted everything based off of the charge, we then came back and sorted everything based off of the size of the atoms. And from that, we were able to put the ionic compounds in order of their lattice energy. Since then, we've introduced a lot of different topics. Well, actually, prior to that, we introduced the concept of ionization energy. Does anybody remember what ionization energy is? The energy to lose an electron to make a cation. The electron affinity was the energy that was associated with the formation of an anion. We made a cation, we made an anion, they came together, and we talked about lattice energy. Some other things, though, that go into the lattice energy include bond enthalpies. We have to be able to break some bonds. In order to create those ions. We have to sublimate a solid. And this goes back to one of the first things we talked about related to states of matter. And you can do sublimation from going from a solid into a gas. All of this comes into lattice energy, along with the enthalpy of reaction. To illustrate the degree that lattice energy plays in the formation of an ionic compound, we can create what's known as a Born-Haber cycle. The Born-Haber cycle is simply a series of hypothetical steps that represents the formation of an ionic compound from its constituent elements. When we're working with the Born-Haber cycle, we are going to know the energy of every step in the process except for the lattice energy. And in reality, the Born-Haber cycle is just another way of working with Hess's law. To take the elements in their standard state and convert them into an ionic compound. It's Hess's law because, again, we add up a series of steps in the process of creating the ionic compound. We add up their enthalpies in the process of creating an ionic compound. So let's look at what those steps are. First of all, we take the enthalpy of formation of the ionic compound, being an enthalpy of formation, it means we're working with the elements in their standard states. And so what we're doing is we're essentially calculating the enthalpy of the ionic compound. The enthalpy of formation of the ionic compound is equal to the enthalpy of the various steps of the Born-Haber cycle. Step number 1 involves subliming the metal solid into metal gas. That process is going to require that energy be added to the reaction. So this is a plus value. The second step is going to be to take the non-metal, many of which are diatomic elements, and it is going to involve breaking a bond. This is where we get the bond energy. It's also going to be positive because you have to add energy to break bonds. The third step is going to be to take that gaseous metal and convert it to an ion using the ionization energy. And ionization energies are always positive because you have to add energy to rip off an electron. So you can quickly see we have 3 positive steps. Now, and those positive steps take a lot of energy. Now we do get back a small amount of that energy when the non-metal is converted into an anion using the electron affinity. But an ionic compound will not form without the highly negative lattice energy. It will not form without that magnetic attraction between the cation and the anion. That is where the majority of energy comes from to make the formation of an ionic compound a favorable process. So what we're going to do is we're going to look at a couple of Born-Haber cycles. The first Born-Haber cycle is going to be that of sodium chloride, which is a +1 -1 ionic compound. The second Born-Haber cycle we're going to look at is going to be that for magnesium chloride. Magnesium being a +2, chloride being a -1. What you're going to observe is that the lattice energy is the driving force behind the formation of these ionic compounds, and in fact, the lattice energy for the formation of magnesium chloride is larger, significantly larger than that for sodium chloride. Now, before we get into the Born-Haber cycle, again, we can calculate the enthalpy for the lattice energy by taking the enthalpy of formation for the ionic compound from its elements in standard state and setting that equal to all of the energies that go into the formation of the ionic compound. The sublimation of the metal, the bonding energy associated with the non-metal, the ionization energy of the metal to form a cation, the electron affinity, which is the energy associated with the formation of an anion, and then the lattice energy. We can look up all of these details, and that will allow us to calculate the lattice energy. So again, the lattice energy is equivalent to all of the energies. I'm sorry, the enthalpy of formation is equivalent to all of those energies that go into the formation of the ionic compound. I'm going to blow up bits and pieces and move this around. We think of the formation of sodium chloride, solid, from its elements in their standard state. The element in its standard state for sodium is a solid, and for chlorine, it's a diatomic element. This is the delta H formation. Now, to get there, the first thing that has to happen is that this sodium has to be converted into a solid, or from a solid into a gas using sublimation. It's a positive step. The second thing that happens is the diatomic chlorine is going to dissociate into its atoms. That process is the bond energy, and it's a positive step. The third thing that's going to happen is we're going to take that sodium metal and we're going to ionize it to form sodium ion. That is the ionization energy, and it is a positive step. 3 positive steps. Now, the nonmetal is going to gain an electron in its electron affinity to form an anion And we get back a small fraction of that energy. But compared to the energy we had to put in, that small fraction does not explain why an ionic compound forms. The only thing that explains why an ionic compound forms is an extremely large lattice energy. The lattice energy, folks, is the driving force behind the formation of an ionic compound. We can look up the energies of these processes. The delta H of formation for the formation of sodium chloride from elements in its standard state is a negative 411 kilojoules. We can look up the sublimation of sodium metal into sodium gas, and that requires 108 kilojoules. We can look up the bond energy associated with the breaking of the chlorine bond to make chlorine atom, and that's 122 kilojoules of energy. We can look up the ionization energy for sodium to form sodium ion, and that's 496 kilojoules of energy. And we can look up this chlorine, and that's a negative 349 kilojoules of energy. So let's figure out what the lattice energy is. So we have a negative 411 kilojoules. That's equal to 108 kilojoules plus 122 kilojoules plus 496 kilojoules minus 349 kilojoules plus the lattice energy. And what we find out is that the lattice energy for this process is a negative 788 kilojoules. Yes.
Is there any significance to the use of the standard identifier in the first two numbers and not in the subsequent numbers? We have to not.
Okay, that probably shouldn't have been a knot. It should have been just a regular. It's a typo. It should have been just the delta H of sublimation. Because remember what the knot stands for. It stands for elements in their standard state. So once we start getting into these reactions, we could say this is in its standard state, and yes, we could look up the delta H of formation. We could say this is in its standard state, we could look up the delta H of formation, but these others would not have an enthalpy of formation. They would not have a standard state. Okay. Magnesium chloride. The net reaction for the formation of magnesium chloride is magnesium solid reacts with chlorine gas to form magnesium chloride. This is the enthalpy of formation, which is a negative 642 kilojoules. Now, there is more to the formation of magnesium chloride because first, yes, we are going to sublime our magnesium. to go from magnesium solid to magnesium gas. That is step number 1. That is going to be its enthalpy of sublimation. Yes, we are going to take chlorine gas and we're going to convert that into 2 chlorine atoms. That is going to be the bond energy. It also requires energy, but with magnesium, we have to take magnesium gas and convert it into a +1 charge. That's the first ionization energy. And then we have to take magnesium +1 and convert it into magnesium 2+, which is the second ionization energy. So magnesium has to go through 2 ionization processes, both of which are going to be positive. Just like before, when we take our chlorine and we add electrons, we're going to get chloride, and that is a negative process. But if you look at all these pink arrows, we're adding a lot of energy, and we don't get back very much. This is the electron affinity. The only reason the ionic compound forms is the lattice energy. And when we take magnesium cation and we add chloride anion to make magnesium chloride, the lattice energy is a negative 2,524. Compare that to the 788 with sodium chloride. As I told you when we were just doing trends, the bigger the charge, the bigger the lattice energy. The reason the bigger the lattice energy is because it has to overcome all of this positive. And there is more positive to it because we are going through more than one ionization energy. Questions about lattice energy? I will say the reason I brought lattice energy in, it's not going to be on the exam form. The reason I brought lattice energy in is because I want you to see that we have been building up to this all semester long. We talked about ionization. We talked about sublimation. We talked about bond energy. We talked about ionization energies and second ionization energies and third ionization energies. We talked about electron affinity. We talked about enthalpies of formation under standard conditions. Now, with all of that combined, we can actually talk about the entire story behind the lattice energy. And hopefully it makes more sense now than it did when you simply had to memorize some trends. There's more to the story. And now you can tell the entire story about the formation of an ionic compound. I originally thought about putting this on the test, but this test is long. And so since I've already tested you on ionization energy in some form, I didn't want to test you again. But now you know the whole thing. Question. We are done for today. up at 3 in the morning. Usually it's around 7. Because I wake up at 3 in the morning. My husband, who doesn't need quite as many hours of sleep, he goes to bed about 9. And he still gets up at 3. And so I changed my schedule to be 6 7. Well, but you shoot back your bedtime and it's not as big of a deal. Sometimes, I also though was one of those that if I didn't get, I usually got my second boost of energy if we could do something, but otherwise I'd be asleep at 10 o'clock. It is easier for some people, it all depends on how mathematically inclined you are. But yes, this test seems to be easier for some because it is mathematical. It is long because you've got to write out everything. But that's why even though I've written the test, I'm gonna take the test and see how long it takes me to. And I will write out everything I expect you to write out and proportional, do it proportionally. You too.
Oh, that's for nursing along.
Okay.
We're doing this problem, and then this is the work that you get, and all of them for like. So we for that one, we flipped it and then multiply by 2, and then for the other one, we just or divide by 2 or something. And
So I'm going to divide the 2 almost by 2.
No, usually that,
And 2.
in my heyday, I used to be really good at words. Now
I will flip that top one and divide it by 2. And 3 and I would have left the middle one, but I would multiply by 3 units.
okay, that's what we were saying. And he didn't do anything because he was like that balances out already.
Right, so that's the error. It's you would have to multiply it by 3 halves in order to get 1. Wait, no, you didn't. Because there's an NO there. 1 NO plus 2 NO is 3 NO.
So we need to like write out the equations before we do all of them. It's like before we didn't write out the equations, we just like that we were like, oh, we need 3 of these, so we multiply this by 3 halves. And then we would put all the equations together. And then if it doesn't equal out, I guess you'd be like, oh,
You had to write out the equations in the correct format.
okay.
Because you needed to see that that NO adds up to that, adds up with that NO to make 3 NO,
Okay.
which I missed the first time because I only looked at.
Yeah. We're just confusing.
Do you need me to write it out? Makes sense?
I think I got it. I understood what he was saying, but in class, like we didn't go over the like, oh, if it already has this many, then you don't have to do that. We kind of just were like, you do all of this and then it can check out.
It got, I chose ones that were looking.
Yeah. And sometimes he just like, he learned things differently than how you teach them, so it just like, it's a little different, but
Understand?
I understand now. Thank you.
Not a problem. But yeah, I've got some problems in the optional homework where you're gonna have to add them up to make it work.
Okay.
Did y'all have questions? For me?
No, I'm just trying to register for one today.
Ah,
Use the sign.
okay. Oh.